please put your message in chat. So I'm just going to start by introducing our speaker today. Dr. Navessin has been around for many years. He is professional with the specialization in research and commercialization of energy materials and sustainable bioproducts. He has experience as a scientist in hydrogen fuel cell and related fields for many years, has worked in the lab, has worked as a manager of multi-party projects in different fields and different areas related to the materials and the scale up of the materials. He has also been involved in commercialization of the materials for hydrogen industry. So I'm just going to cut it short as far as his bio. I'm sure he's going to address some of his experience in the past, and we'll be looking forward to hear his talk today. Dr. Navessin, please.
Thank you very much, Courage, and thank you, Linda, for your invitation to speak here. I like to begin with the next slide here on the accelerated materials design and scale up. So I wanted to outline some of the topics that I want to cover with you. I'm happy to be here. A few things that I wanted to cover today. First, I wanted to discuss about the global perspective of hydrogen demands, understand why hydrogen and why accelerating the material, so the need to accelerated materials design. And then the third bullet point, I wanted to dive a little bit deeper into the materials properties relationship in order to understand the complexity of how and why we need to do the design properly and the complexity of it, and why is it not an easy field to navigate in. And then I'll talk a little bit about materials intelligence flow. These allow us to understand the flow of material from the upstream material development to the downstream device and deployment. Some of the challenges around scaling up of the technologies and accelerating research in the and the future of labs before I finish. So the next slide will show that next I'll dive into the global perspective of demand. Okay, please go to the next two slides. Slide number 5. On hydrogen from a global perspective, this is a very compelling research and report from the International Energy Agency in 2021 outlining.
Sorry, Titichai, just make sure. I don't see your slides are moving from the first one.
Oh.
Okay.
Does it see?
Making sure. Adiola is doing it.
Yeah, Adiola has advanced the slide, and on my screen it shows on the slide 5 now.
Okay.
Does anybody see slide 5 too?
No. Yeah, I can't see it, but that's fine. Everyone see it.
If anybody has a issue, please raise it. Yeah, thank you. So I'll continue. That's okay. So from the global perspective, in this slide shows that projection to meet net zero emissions scenario by 2050, globally we have to change. Globally we have to move towards decarbonization. Electrification is projected to increase dramatically. The use of hydrogen it will be increasing dramatically. So if you look at this the screen from the left figure, you can see that trend that I marked up on the graph. Electrolytic hydrogen on the middle figure is expected to play a significant role in that. And the pie chart on the right shows you that the emission reduction or the impacts of each of the component, they're quite profound, right? Electrification will contribute to 19% of overall. renewables will increase, and I'll talk a bit more in the next few slides. But what I want to draw your attention to is the technology performance and the hydrogen mix. That account to 19% of the overall. These are driven primarily by energy materials and the need for us to do this. Right. On the next slide, please. The driving force behind, on the next slide here, the driving forces behind all this, there are quite a few, right? We alluded to that the cost of renewables will be coming down significantly, and it already start to do so. So this graph on the left by IRENA, the renewable energy report here, has shown that in the recent years and recent decades, the price of renewable has significantly come down, and we know that the trend will continue. Could you go to the next slide, please? Perfect. Okay. So the next one is about hydrogen production pathways and the price, right? So if you look at 2020, that's where we are now. Most of the blue and green hydrogen, these are hydrogen that made from electrolysis. The blue and green are blue hydrogen ones that has that made from 100% renewable electricity with carbon capture. Sorry, the green hydrogen is the one that made from 100% renewable with carbon capture. The price will come down significantly over the years, and that's expected, and that trend should continue. Gray hydrogen price will go up, and this one is the gray hydrogen is the one that made from steam methane reforming, SMR. So with the carbon pricing increasing, this is the trend that we'll see. Right? So in order to make this a reality, significant changes in the materials must happen. So that goes to the next slide, please. I'd like to talk about electrolysis technologies. So there are currently 3 in the pipeline that is realistically be able to deploy. The alkaline water electrolysis, AWE, is an old technology with the advantages and disadvantages as outlined. It's the old and bulky materials, but it's fairly reliable with low performance, low current density, and low operating pressure. That's the drawback. So the footprint is very large. The return on investment on these type of technologies is not that great yet. Now we move forward to the proton exchange membrane water electrolysis, PEM water electrolysis. This is fairly more mature with the use of Nafion or perfluoro membranes. In this type of system, it allows it to have much higher power density and performance, but with some significant drawbacks. Components are expensive. The use of platinum noble metal catalysts increases the cost, and high corrosion atmosphere that drives the use of other materials that has to be of corrosion resistant. This technology is mature enough to be used in the early deployment. However, it is, as I will show, that it is not going to be able to deploy widely. So deployment at scale using this technology would be a significant drawback. An emerging technology using alkaline anion exchange membrane water electrolysis is shown on the right. This is still fairly early, and it is made possible by an ultra high stability, alkaline stability membranes materials that just be able to available in the market recently. In the past, maybe about 7-8 years also. And this unlocked the entire field of alkaline AEMWE technologies, allowing these material to be penetrated and allowing the components and system to be now beginning to develop. So essentially, the advantages that we've seen in this chart is really enabled by breakthrough materials in ion conducting polymers as well as electrocatalysts. And the disadvantages or the challenges remaining is we need better materials. In the next slide, I will now move on to discuss the need for accelerated material design. And we are going to the slide, yes, on the green hydrogen at scale. So just to sum up, right, the challenges is to be able to have green hydrogen at scale, energy storage and conversion, it needs to be better, faster, and cheaper. Specifically, we know that the green hydrogen is about 3 times more expensive than what it needs to be, the target price. It's more expensive than the blue and the gray hydrogen currently. The level of deployment overall globally is less than 2%. Typically, or historically, it takes about 12 to 15 years for materials to integrate down from discovery and the lab stage into the device integration. And we've seen this in PEM fuel cells, and we've seen this in electrolysis. With the success rate of materials be able to penetrate of less than 1%. So it's risky, it's expensive, and it's long, right? That needs to change. How do we do that collectively? So the next slide shows material requirements for deployment at scale. I alluded to earlier that the use of platinum group metals are quite price prohibitive. In addition, environmental concerns around mining of those type of materials, it will be increasingly more constrained on that part. So supply chain will be somewhat more difficult to navigate. The cost overall, both capital investment, upfront CapEx, and the operating costs ongoing needs to come down for a given technology to be able to deploy at scale. Environmental concerns is another factor. We have heard quite widely now about PFAS, fluoro-containing polymers. So the materials that need to be used here cannot be PFAS-containing polymers. Nafion and the current generations of proton conducting polymers definitely will be phased out, right, as we know it. Timeline to deployment. If you look at the graph shown here in various sectors, the pharmaceutical industry, once it clear the approval for use, you see the uptake steadily growth until the patent runs out, and then it kind of falls off. Aerospace, quite similarly, once it's launched, it go through a sales cycle. But in the chemical industry and material industry, typically it takes a long time, so this slow growth amount to over 10 years before materials finds its application and usage widely. So it's a characteristic of materials commercialization, but we have seen that there are more tools available, and the community and the industries are more connected. So this trend is expected to change, right? So commercialization is expected to be much faster. Next slide. It's then point to accelerating materials to device integration for hydrogen. And so I'm just gonna switch gear and deep dive into the complexity of materials in the next slide for the complexity of material and properties relationship. So if we go to the slide, that talks about where and how to seek acceleration. One slide back. Yes, thank you. So where and how to seek accelerations. If we look at materials from the early stage of invention at intrinsic level, and we propagate our way down to downstream integration into materials at micro scale, mesoscale, and then integrate that into component. In this case, from the membrane and catalyst down to catalyst layer, and then to the catalyst-coated membranes, which is at the mesoscale, to membrane electrode assembly at the macro scale, and to cell and stack level at the device and product scale. We've seen that there are different research and development questions that need to be answered along the way, right? And those are shown in the blue box, right? You make the materials better, you understand how they function, etc. All the way down to testing and demonstration. So there are interplays between the intrinsic properties and the properties at different length scale here that we need to understand. The next slide shows that integration of material downstream at the component level, the catalyst-coated membrane is typically a focal point because this is where reaction happens. This is where catalyst ionomer interacts at the three-phase interface and generate reactions. So the rates happening here, the heat, the gas, everything happens at that interfaces. And so at this interface, typically the integration at this stage comprise of the fabrication of catalyst-coated membrane or gas diffusion electrodes, depending on the approach and design at the end. You start off with catalyst material, ionomer, and dispersion media, and it's go through a process of mixing it, and then it get deposited via a deposition process, either by a lab scale process of spray coating or screen printing or a simulated roll-to-roll. And then you go through a process of bonding and drying, right, to achieve the component. Now, this seems fairly straightforward, and it is a simplistic view of it. There are many steps along the way and interactions, which if you go to the next slide, it talks about the fundamentals of this or the models of this with the equations that, essentially current density, exchange current density, it's a function of loading of the catalyst, catalyst utilization, transportation, and composition of each of the phases. Right? I won't dive into this theoretical details too much, but just to show that there are interplays between parameters. Right? In the next slide, I would like to give a little bit of insights into how designers think of this. Right? In the catalyst layer, because you need three functions to happen simultaneously in order to create reactions for electrolysis of reactions or fuel cells, right? So both oxygen evolution, oxygen reduction, hydrogen evolution, and hydrogen consumption. That requires electronic conducting phase, that's protonic conducting phase, and gas. So if we invoke percolation theory, this means that when you have a Borg property, the conductivity or conduction of that phase is equal to 1. Right? But typically, so from the design point of view, you start with 0 and you start adding a particular phase. So let's say for carbon, when you start adding particles of carbon into the box, you have no conduction until you reach a critical point. That's xc. And then the conductivity goes up as a function of volume fraction until you reach the Borg phase. And you have to do that with the 3 phases. Unfortunately, the space is limited. So the volume fraction of the 3 is now hovering between, has to be in between above the critical point, but not too close to it, but can be at the Borg because of the requirement of other phases. That means an optimal use of the catalyst layers that requires basically a balancing act between the 3 composition, knowing that the effective structure and the conduction of each phase. How do we do this, right? This is from the mechanical point of view, as well as from the chemistry point of view. The next slide talks about conducting polymers in this case. So if you think about adding the volume fraction of polymers in the catalyst layers, typical catalysts, typical ionomers used in the catalyst layers are perfluoro sulfonic acid membranes, such as Nafion. There are many equivalents or analogs, alternatives, including Equivian by Solvay. These are shorter side chain types of polymers that has higher crystallinity and thermal stability. So there are some derivatives or improvements that has been deployed as well. Now, on the next slide shows some of the impact of integrating Nafion into the catalyst layer versus using Equivian or alternative short side chain. The figures in the middle shows you that when the NF mean with Nafion 30 weight% in the catalyst layer, and AQ mean with Equian 30 weight%, 20 weight%, and 40 weight%. You can see that when you increase the volume fraction of ionomers, it affects multiple factors here. First one on the left is it affects the servo dynamic diameters. So dispersibility of the catalyst particles in the ink stage before you deposit changes. It also affects the porosity after deposition. And that's quite evident when you look at the scanning electron microscope on the top view, which is in the top middle part of the slide, or the cross section, which is at the top lower fold of the slide in the middle. Now, these also have impacts on the Toffer plots or the kinetics of the catalyst layer itself. So it modifies the catalytic activity. It also has an impact on the resistance, the overall. So the electrochemical impedance spectroscopy on the top right shows that. The next slide, I'll talk about also the impact of dispersion media on the ink. So in addition to the materials, dispersion media that we use to disperse both the catalyst particle and the ionomer has a strong influence on the particle size and the size distribution. If you see the figure on the right, it's a systematic investigation looking at the different dispersion media from isopropanol down to hexane. So different indexes here, right? And the particle size increases as you decrease the diffraction index. So the point being made here is you can disperse the polymer as particles, which it shows on the as a cloudy bottle on the left there, or as a colloidal dispersion, or as completely dispersed, almost like solution like on the right. So the knowledge of being to disperse properly and evaporate quickly has been used in the past, and we've shown, or I've shown in one of the projects, that we can actually improve the production time by 5-folds by selecting the proper dispersion media. The next slide shows some of the designers' thinking of how we go about improving the overall cost of the catalyst layer. So this is in the context of fuel cells, PEM fuel cells, where we use loading of platinum group metal, PGM. In this case, is a combination of platinum and other alloys. We're going from the high polarization, or the baseline polarization at 1, where we start with about 0.25 milligrams of platinum catalyst, platinum-based catalyst per square centimeter with Nafion ionomer. We reduce the loading down without changing anything else. You get quite a big hit in performance, and then you can use various tricks by enhancement of modified ionomer in order to bring the performance back up again, right? And so by tweaking this, you can actually optimize the catalyst layer. So this is only a simplistic view of catalyst layer maximizing performance, not really optimizing overall. As you can imagine, we are looking at multiple variable parameters in the optimization design envelope. That means in order to do this, we need a massive scale of experiment, and of course, time and resources to do this. And this is just for a specific type of catalyst and specific type of ionomer. So back to the next slide, back to the question, where and how to seek acceleration, right? And I know I'm talking to master degree students and technical students here, but as good lawyers always tell me, the answer is it depends, right? So if you look at the next slide where it says where and how to seek acceleration, then it depends of where and where the performance limiting step in your system is, and how would you go about doing that? And there are multiple ways of tackling this. So we are going back to the same drawing board to say that really it's a complex interplay at multiple length scales, right? That we need to understand and collectively bring all these information together, right? So let's look at this in terms of workflow. What does that mean, and what are the decision criteria that goes into this before we start pinpointing and accelerating? In the next slide, please. Material intelligence workflow. And so the next slide would show you the workflow as a diagram. So on the left side, typically you start off with new materials or predicted properties. And then I show you in a few slides that we convert them into component, catalyst coated membranes. And then that component gets evaluated. Now, to whether it's meet the design criteria, specifications, yes or no, right? If it's no, then it goes back to the drawing board and say, okay, from the structural performance relationship point of view, what does it mean with the input from literature and lab data plus modeling? And in the red boxes with the data analytic and machine learning, that can also help to shortcut it as well. And then if it meets the criteria, it goes down to scaling up and cost analysis. That's one technology readiness level higher, right? So further along the value chain. The question is, to meet the application criteria, what is the framework that we use to go about and deciding that? A successful example that has been deployed in the space of hydrogen and fuel cell is the use of technology development matrix. Been used in the development of fuel cells, PEM fuel cells, quite successfully. The technology development matrix is a tool that translates the market needs of a particular application into technology attributes and then down into technical parameters, right? What do I mean by that? So a market needs would be, you need a fuel cell vehicle that would be able to perform a certain speed and power. So, and you need to basically define that from the market perspective, right? So it's green hydrogen that you need in the context of electrolysis. It has to produce at less than, say, €2 per kilograms with a certain capital investment, operating conditions, and environmental restrictions. And then essentially that's the market characteristics. Then you throw that problem into a group of system engineers and say, okay, what do we need in terms of system characteristic in order to satisfy that application, right? For the PEM water electrolysis, to be able to do that, then you have to define what performance, durability, and efficiency required in order to meet the cost targets. What operating conditions it need to be run at, the windows, and the system requirements. What's the footprint? Right? So with that, then the problem gets translated to research engineers and research scientists and system designers into the technical parameters. What materials, what component specifications would you require in order to drive that system, in order to meet that system performance? And that basically triggers into the application criteria box there. Right? So this matrix is quite a powerful tool in order to provide a direct line of sight of that criteria into meeting the target market. If you go to the next slide, please. And so when you look at technology development as a whole, and you're trying to drive your material towards an applications, then you're looking at a very complex interplay of the technical side, the technology attributes, the market piece, and now we're talking also about resources to get things done, right? In this slide, the technology development matrix, a simplified version, kind of shown on the right. Just give you a feel of that, what it looks like. Essentially, different technical parameters with the existing performance versus the state of the art where it is, and any gap, and then the target that you are driving towards. for different components. The graph on the left, essentially, it shows a matrix of different expertise that you need to require, that you basically slot in various topics and disciplines in order to bring about this technology development. This is all to say that matching expertise infrastructure with the workflow and time is a massive amount of effort, and executing that and driving it down the value chain. All of this for me to say is for a materials, to design a materials and integrate that downstream. It takes significant effort, resource, and time, and risk involved in this, right? So that's just to provide insight into the scope and scale, and therefore it is typically very long for materials to trickle its way down into deployment. In the next slide, I'll show you that after it passed the qualification criteria, it go towards a scale up and some of the criteria and some of the consideration around scaling up. In the next slide, industrial scale up. Typically in the R&D stage, you're looking at fabrication or method of integration that is flexible and tunable, right? And that's what you need in at that stage. But once it passes a certain criteria and you need to scale up for pilot demonstration and beyond, especially deployment at scale, you have to look at something like roll-to-roll manufacturing or something faster, right? So, and at that stage, you really are considering quantity, quality, and cost as the three primary objectives, right? And typically, particularly for roll-to-roll manufacturing, this is quite established and standardized. The critical parameters here involves line speed and standardized width and thickness of the three bullets there. Basically, it's the rate of materials going through your line, right? And of course, a definition of standard quality. What would quality means in the case of ion conducting membranes? That's pinhole free, tolerance in terms of thickness across the variation, etc. So how do you define that? So the scaling up process, going from a lab scale to roll, there's a big transition of the two. And this is an area where I think academic literature has fallen quite short, right? It's not viewed as sexy science, but it's the engineering domain where insight, knowledge, and expertise remain very much within the industry, in the deep manufacturing industry. In the next slide, please. So once you have established the manufacturing process, roll to roll, you basically can map out the process modeling. And the next logical step is, once you know each of the process, precursors of materials, solvents, dispersion media that you need, you can now start mapping out the costs. This is done through the techno-economic cost analysis. It is a fairly well-known area in the social science and in science now, to utilize such tool to do this, right? In this case, you map out the process, and then you're looking at different red boxes that I indicated on the chart, right? So production capacity, That's some of the underlying assumptions about the rates, costs, like labor costs, raw material costs, some of the fixed costs that you need to incur, the equipment costs, and then the summation of all the fixed variable, including opportunity costs and some of the tax implications. That trickles down all the way to the total cost of membrane. Right. So this is just to give you the feel of what this techno-economic cost analysis looks like. Okay, in the next slide, please. That allows, this type of setting allows you then to look at the economies of scale when you produce and breakdown of each of the cost components at low, medium, and high volume. And then the graphs here shows you that the economy of scale when you drive the volume without accounting for the learning curves effect. The learning curve effects, what do I mean by that? It's as we, so in the practical sense, as we increase the volume, the manufacturers would then learn about how to improve efficiencies in various steps. So there's a learning curves that typically accelerate that economy of scale beyond a linear projection here. So that's that. And the next slide, I wanted to maybe give a bit of a concluding what we've known so far, remaining challenges in the field of design, accelerated materials design. Right, we are trying to accelerating how materials is integrated downstream, but there's a lack of sophisticated decision systems and scale up. Right. Overall, there's massive silo in data. There's a lot of knowledge and know-how in various specialized area, catalysis, membranes, etc. It's very silo, right? Beginning, there's a lot of interdisciplinary research and consortium funded by EU and various other funding agency that encourage that silos to be broken down and share, and that's great, right? But ultimately, it's still the discovery to device and scale up process. This domain is still very much driven by human recommendations, and therefore it still has a lot of inertia and delay, right? Well, all hope is not lost. So I'd like to point out to some of in the next slide, some of the accelerating research and future labs activities available. One of the exciting things that we're looking at is to automate and optimize the process of ink formulation leading to the catalyst layer design and catalyst coated membranes. So the ink formulation, as I alluded to in the earlier slide, is a very complex field of science that involve multiple interactions of different dispersion medium, ionomer, catalyst particles, as well as carbon particles. The use of high throughput liquid handling system to handle preparation of samples, together with inline automated characterization with light scattering for particle size distribution, as well as rheometer units to understand the rheology of the ink so that you can fit that to the fabrication downstream or manufacturability. Overall, it's a platform that try to unlock that limiting step in the discovery process. This type of platform should be able to enhance productivity by 100-fold, right? Because instead of human doing the experiment a few set at a time, you can do liquid handling of 100 samples at a time, for example, right? And so this type of system shown in the next slide, there are more and more of that coming in the pipeline. So the slide that shows future of labs in the next slide, on the left, you can see that there's some concept of future of labs where, you know, there's everything is fully automated and you basically send in the jobs and so on. This address significant resource constraints, and it will unlock productivity and solving reproducibility crisis that we've seen in science. However, these type of labs are very domain specific. So this example that I gave is on catalyst layer design only, the catalyst ink formulation. There's very specific in various fields. So the next frontier is really around network of labs or the decentralized cloud labs. This is one exciting project that been recently funded and just starting. It's called Decode, and that's, I will leave that exciting project's details for the next speaker, Dr. Kurosh Malik. Right? So for me, just to conclude that it is a complex field. It is a field that ripe to be automated, and with the invention, with the emergence of AI, machine learning, and future of labs, it is an exciting field to be in terms of seeing the acceleration of progress from this moment on, right? So I'd like to thank you for your time and attention. I'm looking forward to Kurosh's presentation, and I can answer question at the end. Thank you.
Thank you, Titichai. I appreciate your presentation. As for the agenda, I think Linda can also jump in if there is any other plan, but we wanted to have all the questions at the end. So I'm just going to go through some complementary materials to what was presented in a few minutes, and then we come back to all the questions and discussions if any. Before I do that, Linda, do you want to add anything, or I can just move forward with the next few slides that I'm just going to present? If not, okay. Let me just share the next set of slides. Hopefully you're able to see it in full screen. Mm-hmm. Okay, great. So I'm just going to give you a little bit about where I am coming from. Research Center Jülich in west of Germany. A little bit about that. We're part of Helmholtz Association, the largest research association in Germany. We are the largest research center, as you can see, located in the west side of the country, and we are contributing to a lot of different fields within 12 institutes, 88 sub-institutes. About 7,200 people are working in the research center, and our focus is more on the information technologies. We are hosting one of the largest quantum computing and exascale computational capabilities in Europe. In energy, there's a lot of activities on batteries as the satellite sites, huge number of experience and historical advancement in hydrogen technology and also in bioeconomy. So as far as the continuation of the things that was discussed previously, I think what was very important and mentioned a lot in Titichai's presentations was the impact of the scaling of a lot of these technologies that we hear here and there in terms of sort of ramping up more EV technologies, scaling up of the hydrogen from what it is now and at few sort of megawatt scales to gigawatt scales by 2030. So a lot of these things technologically is possible, but of course it's going to drain a lot of resource on the material side. And I think what we wanted to allude here is that it has to go hand in hand to make sure that the type of materials that are used and the new materials is not going to impact the resources. The other elements that is also adding into the whole equation of the cost and performance that was widely, especially on the performance, addressed in the previous slides was also the durability and circularity of the materials. And then if you add supply chain issue, that it's more and more becoming an important aspects of the material used in energy systems, that makes the choice of materials very limited, and also a function of a lot of factors that has to be considered. So I just wanted to make sure today, if you want to go to new materials, are they for the batteries or for hydrogen or chemical energy and e-fuel, it's not about the cost and performance and durability of the materials anymore, and circularity and supply chain security are becoming more and more important into the whole process. So I'm just going to summarize what really the issue that was discussed is that you saw the scale up at the industry scale and the requirements of the certain materials for electrolysis and fuel cell, specifically either as a catalyst coated membrane components or as the electrode assembly, membrane electrode assembly part. Understanding of requirements at that commercial and application scales and combined with what you understand in lab creates a sort of a chasm that has to be crossed, and as we call it, the integration chasm. And this is really well the bottleneck of a lot of research in the lab, bridging into the commercialization lies, and that's where the majority of the effort and the money and cost would be on the R&D and the development side and demonstration side. There's a lesson that we can learn from what happened in the past, apply that to a new era of hydrogen production. If you look at the advancement of the technology of fuel cell since its inception on 1880, where it really came into life in terms of the device functionality of a PEM fuel cell, up to recent years, you have seen an exponential increase of the mass activity of the catalyst that really happened around 1960, not because of the new catalyst. It's the same type of catalyst as platinum that has been used in the past. It's mainly because of inclusion of some components into the mix, as was discussed previously, which we call it ionomer, into the catalyst. And not only it brings the utilization of the amount of the catalyst used lower, and therefore make the whole layer cost effective, it's also adding a lot of functionalities that increasingly and exponentially increasing the mass activity. So if you look at same sort of exponential growth of the catalyst activity for the water electrolysis, assuming it goes at the same rate, the time that we're going to get into that level of the activities basically lies around 2040, 2050. And that's where the acceleration concept is coming from. If you want to basically go from doubling of this mass activity every 6 years to doubling it every 2 years to accelerate, so that by 2030, around that time, we're getting into the target, that's where essentially the acceleration is required. And the project that we're doing with colleagues in Germany and Canada is called German Canadian Materials Acceleration Center, is looking into that acceleration from different aspects. That includes better data analytics. It includes building labs that are able to do synthesis and fabrication faster. And on top of everything, we're trying to do the integration more robust and productive. So conventionally, data has been used a lot in the field of hydrogen, as well as similar fields, either generated through simulations that are done, or the modeling work that are done at the interface of the catalyst, platinum, ionomer, and water, or looking at some data science-based prediction of properties. What we are trying to basically do as the AI-enabled design is to have models that are driven by larger scale of the amount of data that can support recommendation models that which catalysts at what component of the ionomer and similar are able to feed into a catalyst design so that it gives the highest performance required for certain application, either at the megawatt scale or gigawatt scale in case of the electrolysis, or applications in fuel cell, either as automotive or backup power. So they all need different design of the components. The other aspects of the utilizing of the models and data in a different way is basically supporting these automated labs, as we call them, self-driving, all the material acceleration platforms that are able to design materials, components to have the maximum functionality of the device. So I'm going to talk a little bit about this last block of this in this presentation. So what we have basically are looking into these activities as part of this collaborative effort is really understanding of the properties at the interface, which is the key part of the whole system. If you look at batteries and similar electrochemical system, what happens at the interface of the catalysts or active materials in general, it could be metal oxide in batteries and catalysts in fuel cell electrolysis, and the other components, the reactants, everything happens at the interface. And that's an area of research that is still very much needed, more sort of exploration of the properties, and how those properties at the interface is changing determines how these things would fit into the whole spectrum of the development and the scale up. So understanding of that, plus the how the autonomous lab is able to understand. So building autonomous lab is something, making it function to be useful for development of the materials as or better materials, that the state of the art is something else. And I think I just want to emphasize that would require a lot of amount of data and the models that basically support that process. And then if you look at characterization and the performance measurements and durability measurements that has to happen online, hand in hand with this process, it's something to look at basically bucket of activities, as we call it, in the spectrum of the work packages in this activity. So, and then obviously at the end, the data sharing, data understanding of the data flow and optimization of the workflow using those data is the key. So integration has to happen in summary as a scale to scale. So meaning that you have to be able to do integration at the materials to component to cells to devices, and then devices into systems. It also has to happen into component to component. If you have a catalyst layer that you have to match into certain sort of other components, has to have sort of enough integration so that it's not losing any properties. And of course, lab to lab integration is important because a lot of this sort of research are coming from different labs with different perspective, type of data, measurement types, and so on. So an example of the formulation of the ink, if you want to go into sort of optimization of this through some robotic labs, I just put some numbers here for you to understand what we are dealing with in terms of the space of the optimization. So if you look at the ink, I think it was mentioned in one of the slides in the previous talk, we have a lot of parameters at the ink level, the mixing level, at the deposition level, and at the level. So if you look at that, we were dealing with close to 10 to the power of 4 the space of the physical and the materials related to the space. And if you basically are looking into that, add new materials requirements, I think it was mentioned that you have to look at non-fluorinated, for example. It adds complexity due to circularity and the sustainability required. And then it would result into hundreds of thousands, if not less, of if not more of the spaces that you have to be look at. And then it's obviously it has huge amount of the waste of the chemicals and data available there. So really what we're trying to do here is that have 2 order of magnitudes, at least, reduction of the the space of the data, so that you're able to basically do optimization using this self-driving labs. And this is where the acceleration is really coming from. In the context of this acceleration using material intelligence, your source of data is important, and you have to start from somewhere that data is basically gathered, already established. So a lot of the data that comes from, of course, literature is very unstructured. The correlation is very low. Data is not complete. Cleaning it is a big effort. So it's not really the only source you want to look into. Creating of these knowledge graphs that essentially are the bulk of the properties and the type of data and the relationship is relying also on expertise in the human intervention of the data itself, so that you are basically have a good understanding of the systematic data that has to be generated. And without this, it's not really possible to run any of this robotic labs with access to this data, either they're coming from modeling or the public sources and experiments. So on the data side, so systematic data, complete data is extremely important, but of course we don't have always access to complete set of data. So that's why we apply the deep learning techniques to basically predict some of the data. That's what we have done in a lot of different cases, especially for the catalyst for the CO2 reduction as an example. So you can see all type of the catalyst is used to date in the lab space, as well as the commercialization. We looked at all the properties of this, and we were able to basically, using this large number of data, fill in the gap of the data that is not available. For example, if you look at 5 key factors of applied potential, fire efficiency, selectivity, which is the inherent property of this type of catalyst due to different type of products that can result from this catalyst, which is different from the catalyst that used for the hydrogen technology that is specifically geared toward production of the hydrogen oxygen, or production of water from oxygen and hydrogen in case of the fuel cell. In the CO2, we also have some other elements of selectivity of the product and the fuel. And the recommendation model that we applied after cleaning up data that comes from different sources, and then able to basically use that recommendation model and give you top catalyst conditions of the synthesis that basically it would bring depending on the product is important. So this is an example of the deep learning process that you go through to find those part of the data that is actually missing values, so that you're able to run these recommendation models. And without cleanness, cleaning up the data and the completing of the data, you're not able to run this aspect. So having that in mind, the data that created is basically, if you come back to the hydrogen, you're looking at the fabrication data, performance data and measurement data, and data that is related to the physical properties of the materials. And then if you map this into a framework that generate a knowledge graph that I just mentioned earlier, as we refer to that as ontology, or the way that basically data are uniformly discussed and shared along certain buckets of the data from fabrication all the way into the device, it basically gives a good framework to go and do acceleration using these techniques. A few examples of the dimensional of the data. As you saw, the process of the ink fabrication is very complex. It can go through a lot of different things. If you look at, for example, the effect of the catalyst itself, there's a lot of catalyst types and formats are used in literature to produce the best ink. Some examples are here, and you can see even the values of the performance. You have a wide range of changing of the output current density that comes out of this catalyst. And so another example is the effect of solvent, for example, in the ink. If you look at the space of the solvent itself, we're using typically industry is using IPA mixed with water and some other solvents here and there, depending on the technology. But The reality is that in the R&D space, we're looking at a lot of different solvents, and again, it shows the variations of this solvent as a result of their properties and how it impacts the current density and the output of the result. So once you have this data space, basically, and you can visualize and see which type of the range of the current density you're looking for, and looking at certain solvent, you have a good space of the prediction of properties, which can be fed into neural network in terms of the input layer of the ink. I think was mentioned this as well in the previous talk. In the solution the phase, we have temperature, pH, stirring rate, type of platinum carbon, and the ratio, amount of the ionomer to carbon ratio, the solvent types, and so on. That would basically impact the output layer, which would be a viscosity of the ink, the agglomerated structure of the ink, a particle size distribution, and so on. And you have to go through a sort of the hidden layer to see, given the data that you have, how you're able to optimize certain properties. For example, if you want to sort of optimize viscosity, which is important for the durability and uniformity of the catalyst layer, which parameters on the inner layer has to be optimized. And this is, as I mentioned, we're looking into the 10 to the power of 3, more or less, sort of space of the parameters that has to be optimized, that virtually impossible to be done through any sort of mathematical model, and that you have to look at neural network to do it. Now, when we apply that to those, you can see some same sort of activities of the prediction of the best catalyst for certain criteria. They can be resulted from this scheme, as you can see in the spider chart. If you want to look at the target, the catalyst that you're looking for, and you have some sort of catalyst already predicted, it gives you a top 5 catalyst that's basically used here. So once the problem of data really is solved, which is the first step of building any of this sort of automated and cloud-connected labs, we're able to basically orchestrate the process using this data over time, and hopefully be able to match different data from different labs and use that for continuous improvement. So the Project Decode, a newly funded European project that we are involved in, is basically has mandate to look at these aspects of the development of the new type of catalyst for the hydrogen technology by applying a new type of ionomer. The mandate that we have in this project is to do all the process at least 10 times faster. As I mentioned, typically it takes a long time to do this integration from the materials in the lab to the devices, but it's important to basically look at it as aspects at the acceleration of up to 10 times. That is very much relying on these models that I just mentioned. So this is basically typically what we discussed all the way, closing the loop of the on-demand process from the data gathering as well as the automation of the fabrication process of the ink, which is the heart of the commercialization of a lot of devices that is used in the hydrogen technology. So just finish that with some thoughts. Crossing the bridge from materials to device integration is important. And it's not about the accelerating of the development, it's also accelerating the understanding. And as I said, the domain knowledge on the interfaces, and also understanding the impact of non-fluorinated ionomer membrane, which is a new aspects of the materials, is extremely important in this process. And then some other domains also have done a lot of this in the past that we can learn from. And data orchestration is very much relying on generating of high quality and complete data sets. At least in hydrogen, that has been our mandate to develop those, and being also able to quickly evaluate the robustness of those data is important, which is important for prediction of descriptors and optimization framework for the integration and scale up. Okay, thank you very much. Just done with the presentation at this point. I'm going to hand in the whole discussions to Linda. And if or Adeola, if there is any questions or anything we're gonna refer to in the talks. Maybe we'll start with some questions for Titichai. Linda, if you want to take this on at this point. If there's any question, we're able to take it. I think we have about 30 minutes left from the whole sort of allocated time. Give it a few minutes, a few seconds at least. Yeah, so one of the things that I wanted to get a little bit more of insight from Dr. Navessin, who has been involved in applying of his expertise in materials to scale up of the materials for ionomer and similar, is that so how do you see in general the path to replacing of the ionomer with the fluorinated base, with a non-fluorinated base from the state of the art? What are the really main challenges that you see? You have alluded a little bit about this in your presentation, but I want to see from the technical perspective and commercial perspective, the scale up of these materials would play.
Right. Thank you, Kourosh. From the perspective of materials itself, there are a number of promising candidates that are non-fluorinated in nature. So hydrocarbon-based material, hydrocarbon-based membrane. There are a large number of that, and it's in the literature, right? So many of those has shown promises, even exceeding the performance of Nafion as a benchmark. So there are a number of those. Now, as we talk about in this presentation, driving those leading promising candidates down the value chain takes effort and time, right? Even if they have breakthrough materials today, it's going to take some years to do that. Now, hopefully with projects like Decode and accelerated labs, this would not take as long, right? So that's from the perspective of research, that's exciting. From the supply chain itself, fluorinated polymers, precursors of those are being restricted more and more, right? As we know, and so the pricing and availability to make those type of materials would be very limited and very difficult in the coming years. So hydrocarbon-based ionomer and membrane materials is really the way to go, right, in the future. So from that perspective, all directions and all forces point to that's ought to be the way of the future. So this should be a major focus for many of the research topics, integrating new catalysts into catalyst layers, right? To basically investigate using hydrocarbon-based polymers.
Good. Thank you. Is there any other question from the audience or anything, any comments? I'm looking at the chat. Okay, so if not, I want to thank again Dr. Navessin accepting to present a very insightful presentation all the way from the on the materials and also scale up. I hope it has been useful for the demographic of people who are working on different aspects of the materials that scale up in hydrogen. I want to thank also StoRIES that helped organizing this, and Linda specifically, who has been behind the whole sort of organizing this from months ago. I want to thank all the colleagues who have used, and also the participants who have stayed almost an hour and a half and listen to what we presented, and I hope it has been useful for excitement that is in within hydrogen industry and the areas of research that can be explored further, and hopefully has been stimulating that to a degree. Okay, well, thank you very much again, and hope you have a great evening and enjoy the rest of this seminar series in the next weeks or days. Thank you.
Okay, thank you for having me.
Thank you. Bye-bye.